Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
The 8051 microcontroller, it is one of the most popular general purpose microcontroller which was designed by Intel in 1980s. And this microcontroller, it is an 8-bit microcontroller, means it deals with data which is of 8 bits. And it has 40 pins IC and it operates at plus 5 volts power supply. Now this 8051 microcontroller, its architecture, or we can say block diagram, it consists of various components, and in this video we are going to study the functions of each of these components. So let us start with it. Coming to the block diagram, this is the block diagram of 8051 microcontroller. In this block diagram, you can see that there are various blocks, and that block, what it represents, it is written inside the block. So this 8051 microcontroller, it has 8-bit data bus and 16-bit address bus. Okay, data bus is used to carry the data and address bus it is used to carry the addresses. Okay. Now also this 8051, it has 4 ports, and these 4 ports are as various blocks in this block diagram. This is for port 0. Port 0, it has drivers and latch. Both are, each port is having a driver, or we can say a buffer, and a latch associated with it. So these two are for port 0 and these two are for port 1. These two are for port 2 and these latch and drivers, these are for port 3. Now these ports, they are 8-bit ports, so their lines are represented here. These are bidirectional ports, so bidirectional arrows are drawn here, and 8 bits are there, so starting from P0 to P7. Okay, these are the 8 bits. These are the 8 bits for port 2. These are the 8 bits for port 1 and these are the 8 bits for port 3. Okay. Then we have different registers here. Memory is also there. This is the RAM memory and this is the ROM memory. That is random access memory and read-only memory. For read-only memory, we don't have any addressing because we can only read that memory. No data can be written over it. So there is no address register for it. But for RAM memory, we have the address register. We can read or write the data or the program code into this RAM memory. Then we have various registers like A register, B register, temporary registers are also there, arithmetic and logical unit is there, program status word is there, stack pointer, and some special function registers are also there. Also we have the data pointer, program counter and program address register in it. Okay, here we have the timing and the control unit and the instruction register. The timing and the control unit, it provides various control signals like PSEN, ALE, EA, reset. All these signals are provided by the timing and the control unit. Then we have the oscillator. To the oscillator, the crystal is connected, and this oscillator, it is going to generate the clock pulses, and these clock pulses will be provided to the different registers of this 8051. So this was just a short description of the block diagram. We will study the blocks in detail now. First we will start with the ALU, that is the arithmetic and the logical unit. The arithmetic and logic unit, performs the arithmetical operations also and logical operations also. Arithmetic operations like addition, subtraction, multiplication, division, and logical operations like logical and, logical or, logical XOR, and the NOT operations. Okay. So this arithmetic and logical unit, it can also manipulate 1 bit as well as 8-bit data types. Okay. So because this arithmetic and logical unit, it is performing all the arithmetic and logical operations. So this unit is also capable of manipulating the 1 bit, means out of the 8 bits of the data, it can change either 1 bit also, or it can change the 8-bit data types also. So the range of data types will be from 1 bit to the 8 bits. So it can perform operations with all the types of data types, that is starting from 1 bit to the 8 bit. Also, individual bits, they can be set, cleared, complemented, tested, and used in the logical computation. Okay. So this ALU unit, it can also set, it can also clear, complement, and test the bits of the registers. Individual bits of the registers, they can be set and cleared using this arithmetic and logical unit. There are various operations which can be performed other than the arithmetic and logical operations. They can be performed by the ALU unit. Okay. Next block we have in the block diagram was the accumulator. Accumulator, it is an 8-bit register. Here it is denoted in the block diagram as the A register. So this accumulator, it is an 8-bit register, and it is used to hold the data and receive the result of the arithmetic and logical operations. So accumulator, it is going to store the data also, and also the result of the arithmetic operations. Second, next we have the B register. It is shown here in the block diagram: B register, A register, and the ALU. B register, it is also a general purpose 8-bit register. Okay, we can use it as a temporary register also if we want to use it for the like if we are performing the arithmetic and logical operation, and if we want to store the intermediate data, or if we want to perform any operations with the accumulator, then we can also use this register. So this register is an 8-bit general purpose register. Next block in this central processing unit we have is the PSW, that is the program status word. Now there are many instructions which implicitly or explicitly they affect the bits of the registers. Okay, so how these bits are affected of the result, that is shown by the program status word. Okay. So the instructions which implicitly or explicitly affect the bits, they are categorized, or they together form the program status word, and they are affected by the status flags. Now this program status word, it shows the status of all the flags of 8051, and also this program status word, it is used to select the memory bank. So this program status word, it is an 8-bit register. So these 8 bits, they are defined, each bit is defined a specific status flag. So let's see that how the 8 bits of the program status word, they are defined. So the 8 bits of the program status word, they are defined just like this. Bit 7 is the most significant bit, and bit not B0, it is the least significant bit. B7, it is defined as the carry flag. B6 is defined as auxiliary carry flag. B5 is the F0, that is the user defined flag. Bit 4 and bit 3, these are used for the selection of the bank, because 8051, it is having 4 banks are there, or we can say 4 ports are there, port 0 to port 3, or bank 0 to bank 3, 4 register banks are there. So to select each of the banks, we have these selection bits. Okay, then we have overflow flag. Bit 1, it is reserved for the later use, and bit 0, it is for the parity flag. Now if any arithmetic or logical operations, it gives a result in which carry is generated, so this carry flag will be set whenever carry is generated, and it will be reset when no carry is generated. So this program status word, as I have said, that it indicates the conditions of the flags. Okay, so it is indicating that the result obtained, it has generated a carry. Okay, so bit 7, it will be set in the case when carry is generated, and it will be reset when no carry is generated. Next, bit 6, it is for auxiliary carry. This auxiliary carry flag, it is used for the BCD operations. In BCD operations, we have whenever the carry is generated from bit 3 to bit 4, then in that case auxiliary carry flag will be set, otherwise it will be reset. Bit 5, it is the user defined flag. Bit 4 and bit 3, select the working register banks. So there are 2 bits here, bit 4 and bit 3, so they can take different values like 0, 0, 0, 1, 1, 0 and 1, 1. So let's see that how you select the banks. This is RS1, bit 4, and RS0, bit 3. So when these bits, they are 0, 0, then bank 0 is selected. If it is 0 1, then bank 1 is selected. 1 0, bank 2, and 1 1, then bank 3. Okay, so in this way these two bits they select the banks. Okay, next we have bit 2. Bit 2 is for overflow flag. Whenever the arithmetic operation it generates an result which is having an overflow, means after bit 7 bit 8 is also generated. So in this case this overflow flag will be set. Okay, next we have bit 1 which is reserved. And then we have bit 0 which is the parity flag. Parity flag, it indicates that the number of ones in the number, means an arithmetic or a logical result will have 8 bits. So that 8 bits, out of that 8 bits, the number of ones either they are even or odd. So if there are even number of ones in the result, then this parity flag will be set, and if there are odd number of ones, then this parity flag will be reset. So it will be 1 when we have even parity, and it will be 0 when we are having odd parity. Okay, so this was the program status word indicating the status of the various flags of the 8051. Next register we have, or next block in this block diagram we have is the stack pointer. All these what we have studied, the arithmetic logic unit, A register, B register, PSW, and special function registers and stack pointer, they all form the central processing unit. So next is the stack pointer. Now in the memory we have a different array, means there are a block of memory locations which can be used as the stack. Now this block of memory locations, they are used to store either the data, means if we want to store some addresses or some data in between of the execution of the main program, or subroutines if we want to store, then all this data and the subroutines they can be stored in the stack. Now the address from where the stack is starting, that is pointed by the stack pointer. Okay, so this stack pointer, it will be a 16-bit register which is pointing towards the starting address of the stack. So as the stack, it is holding the data also and the subroutines also. Subroutines are short programs which are written in the stack, means which are written at different locations, and these short programs or subroutines, they are called in the main program. So for storing the data we have the push instruction, and for storing the subroutines or calling the subroutines we have the call instructions. So this stack pointer, it is incremented before data is stored using push and call instructions. So if we have just like this is the stack in which the memory locations are there, and stack is starting from this. Okay, so the data if it wants to store, then this stack pointer, it is pointing towards the starting address of the stack. So this stack pointer will be incremented, and after that data will be stored into the stack. Okay, so this stack pointer is incremented before data is stored using push and call instructions, and after reset the value of stack pointer is 07H. When the microcontroller is reset using the reset instruction or reset pin, then this after reset of the microcontroller, this stack pointer will be initialized with this value 07H. H means that this address, it is in the hexadecimal notation, so the address is only 07. Okay, so it is initialized with this address 07. 7. So stack is going to store all the data from this memory location. Next we have is the data pointer. In the block diagram you can see we have the data pointer dptr. Okay, this data pointer, it will point towards the data. Okay, because in the microcontroller we have program memory also and data memory also. So to hold the address of the memory location of the data, we have the data pointer. So this DPTR, that is data pointer, it is a 16-bit register which is used to hold the 16-bit address of the data memory. We have two memory in microcontrollers, data memory and program memory. So to hold the address, 16-bit address of data memory, we have this data pointer register. Now this DPTR, it is divided because it is of 16-bit. So it can be divided into 8-bit register, which is DPH and DPL. These are 8-bit registers. If we want to store the 8-bit address, then we can use either DPH or DPL. DPH means higher order data pointer and this is lower order data pointer. Now this 8-bit pointers, that is DPH and DPL, they are used for accessing the internal RAM and the SFR. SFR means the special function registers. So if we want to address this internal RAM and the SFRs, then we will use the 8-bit pointers, because the addresses of the internal RAM and the SFR, they are 8-bit registers. So for 8-bit addresses, we will use the DPH and DPL, and 16-bit registers or 16-bit data pointer, it will be used for accessing the external memory. Okay, so it can be used as 16-bit also and as 8-bit also. Now the contents of the data pointer, they are programmable using the instructions. If we want to read the contents of this data pointer, or if we want to alter this, if we want to load this data pointer with some address, then we can use this all with the help of instructions. Next block we have in the block diagram is the program counter. Here we were having data pointer, above it we have the program counter. Now the function of this program counter, it is used to store the address of where the next instruction is written. It is a 16-bit register, so it will hold the 16-bit address, and that address will be the address of the memory location where the next instruction is written. So when the microcontroller, it is executing the instructions, it will get to know that where the next instruction is written, so that sequence of execution of the program, it will be continued. Okay. So program counter, it is a 16-bit register and it is used as the address pointer to access the program instructions, and it is automatically incremented after every byte of instruction fetch. So whenever the instruction is fetched, the program counter, it will be automatically incremented and it will indicate towards the next instruction. So this was the program counter, which is the 16-bit register. Next block we have is for the input output ports. In 8051 microcontroller, we have 4 ports which can act as the bidirectional input output ports. Bidirectional means they can act as an input port also and as an output port also. So these 4 ports are port 0, port 1, port 2 and port 3. As each port, it is of 8 bits, so port 0 also we will have 8 bits from 0 to 7. We have port 1, for port 1 also 0 to 7, for port 2 also 0 to 7, and for port 3 also we have 0 to 7. So these are the 8 bits for the 4 ports, so we will have total 32 bits which can act as the input output ports or input output pins. Okay. Now for each port we have a latch and a driver. Latch is used to if we want to latch the input or output of the port, or if we want to give the addresses of the port, then we can use the latch. And driver, it is also the buffer, so it is used to amplify the input of the ports. Okay, so each port has a latch and a driver. So in the block diagram also you can see that for port 0, 1, 2 and 3 we have the drivers also and we have a latch also. So two blocks are associated with each of these 4 ports. Now this port 0, because in the microcontroller we have the external memory also and internal memory is also there. So whenever external memory is present in the microcontroller, then this port 0, it can be used as the multiplexed lower order address bus and the data bus. So whenever the external memory is present, port 0 will act as multiplexed low order address bus and data bus. That means it can act as AD0 to AD7. A is for address, D is for data, and we have the 8 lower order address bus. So port 0 can act as both. Similarly for port 2, it will act as higher order address bus. Higher order address bus means from A8 to A15, because we have the total 16-bit address bus. So 8 bits are for the lower order and 8 bits are for the higher order. So port 2, it can act as the port 2 input output pins also and as the higher order address bus also. So whenever external memory is present, the function of port 0 and port 2, they will be changed. Then we have port 1. Port 1, it has only the single function. It will act as only the general purpose input output port. There is no second function for it, just like the port 0 and port 2. Port 1, it is defined for input output pins only. So we can say that it is a dedicated input output port. And it does not have any alternate function. Now port 3 pins, they can be used for serial communication also, like serial transmit and receive, for the interrupt pins also, for timer and counter pins also, and for the read and write signals. So port 3 also has dual functions. It can act as input output pin also and as the external signals pins also. So this was the input output ports of the 8051 microcontroller. Next, in coming to the architecture block diagram, this block we have already studied, which comes under the central processing unit. This block we have already completed. This was the ports, and next coming to the instruction register and the timing and control unit. Now this instruction register, whenever the microcontroller it executes the instructions, so it is going to convert that instructions in the form of code, and that code will be first decoded, means instruction will be first fetched, then decoded, and then it will be executed. So whenever the instruction it is fetched, after that it will be given to the instruction register where it will be decoded, and whatever that function is associated with that instruction, if any control or timing signals they are required, those will be provided by the timing and control unit. So instruction register, it will fetch the instruction and then decode it and provide that decoded instruction to the timing and control unit, and timing and control unit, it will provide the control signals, internal or the external. So microcontroller, it is going to fetch the instructions. Okay, it is going to fetch the instructions from the memory where it is written, and from that memory it will first get the address from the program counter where the instruction is written. So address is there and instruction is stored at that memory location. It is going to fetch it, going to decode it and provide it to the timing and control unit. So you can see here that microcontroller, it fetches the instructions one by one, starting from the address stored in the program counter and store it in the instruction register, which decodes the instructions and give information to the timing and control unit. And using this information, timing and control unit generate the control signals. So using this information, timing and control unit, it will generate control signals which are necessary for the internal and external operations. You can see in the block diagram that the timing and control unit, it is generating the control signals like PSN, that is program store enable, ALE address latch enable, EA, that is enabling or disabling the internal and the external memory, and RST is for resetting the microcontroller. So these are the timing and control signals which are generated by this unit. Next we come to the timers and the counters block. timers and counters block is present here. We have two timers in the microcontroller, that is timer 1 and timer 0, and these are 16-bit timers. And for these timers we have these timers or counters, they can be operated in different modes. So we have different special functions registers also there. Okay, so let's come to the timer, counter and the serial ports block. So 8051, it has two 16-bit timers and counters. So there are two 16-bit programmable because we can program these timers and counters in different modes of operations. So there are two. So one is the timer 1 and timer 0. Now these two 16-bit registers, they can act as timer also and as the counter also. So in the counter mode, they are going to count the transitions, that is we can load the counter with the count value, and this count value will either be decremented or incremented. Okay, like suppose if we have loaded the counter with the value 10, and we can increment also it and decrement also it. Like if we want to decrement, then decrement it up till its value reaches to 0, and increment also, suppose we can load it with the value 0 and increment it till the value 10. So these counters, they are loaded with the count value and they can be incremented or decremented. So this was the operation when these 16-bit registers, they are acting as the counter. Now in the timer mode, now in the timer mode, because we are having the various timers like timer 0 and timer 2, we will have two timers. So these timers, they can be used to operate in different modes. There are four different modes: mode 0, mode 1, mode 2 and mode 3. So in the timer mode, these timers, they can be programmed to operate in the different modes of operations. Like they can act as serial ports also, for serial communication also, for receiving and transmitting the data also. So in the timer mode, we can program these two timers to work in the different modes. So there are these two 16-bit programmable timers and counters. They can act as counter also and as the timer also. In counter modes, they will perform the counting operation, and in timer mode, they will be operating in either of these four modes: 0, 1, 2 and 3. So let's see that what will be the operation of these timers in these four modes. In mode 0, because we have written here that timers and counters and serial ports. So these timers, they can act as serial ports also. So in mode 0, So the functioning of the serial ports, it is linked with the timer modes. If the timers are operating in mode 0, then the serial ports, they can either receive or either transmit the data at fixed baud rate. Baud rate means the bits which are transferred per second. Okay, so baud rate, it is the rate at which the bits are transmitted. So bits per second, how many bits are transmitted per second, that will be the baud rate. So at fixed baud rate, the serial ports, they can either receive or either transmit the data. Whereas in mode 1 and mode 3, timers can work So the serial ports, they can work as full duplex serial ports. Full duplex means they can receive also and they can transmit also at the same time. So with the variable baud rate, in the case of mode 0, we were having fixed baud rate, but in mode 1 and mode 3, we have the variable baud rate, and this baud rate can be decided by programming the timer 1. Okay. We have mode 2 also. So in mode 2, the serial ports, they can simultaneously receive or transmit. They can simultaneously transmit or receive at any one of the two selectable baud rate. So the difference between the four modes is that either the serial port, it is working as full duplex, half duplex or simple port, and what will be the baud rate. In mode 0, it will act as simple serial port which will either receive or either transmit, and the baud rate is fixed. In mode 1 and 3, baud rate is variable and the port is acting as full duplex. In mode 2, it is acting as full duplex, but the baud rate is either one of the two selectable baud rates. So next block we have in the block diagram is the memory. Okay. So memory in the microcontroller, we have the read-only memory also and the random access memory, that is RAM and ROM. And the memory, it is divided into two parts, that is program memory and the data memory. So here we have the blocks for ROM and RAM. RAM, because we can address the RAM memory, so we have RAM address register also, but we cannot address this ROM memory, it is only for the reading purpose, so this have only the one block. Okay, so let's study the memory organization in 8051. So when we studied the pointers in this 8051, we studied that the program counter, it is also a 16-bit counter, and the data pointer is also a 16-bit pointer. So as these pointers or the address pointers, they are of 16-bit, so this 8051, if we calculate its memory size, then 8051 memory size, because 16-bit is there, so 2 raised to the power 16, it will come out to be 64 kilobytes. So it will have 64 kilobytes of the program memory. Now microcontroller 8051, it requires both the RAM and the ROM, that is EPROM, okay, and RAM also is required. Now ROM is required for the permanent storage of the programs and the data, whereas RAM is required for the temporary storage of the data and the programs. Now, as all the programs, they will be stored, if we want to store the temporary or the short programs like the subroutines, we will store it in the stack. So stack is used for the temporary storage of the programs. So stack and data, they will be stored in the RAM, whereas the permanent storage of data and the program, it will be done in the EPROM. Now in 8051 we have a signal which is called PSEN, that is program store enable. So this program store enable signal, it is used to read the data from the EPROM. Okay, whenever we want to read this data, we will make the PSEN signal low, and because PSEN, it is an active low signal, so a microcontroller can read the data from the EPROM using the PSEN signal. So this EPROM, because its full form is read only memory, so only read operation can be performed in it, and this read operation is performed by using this PSEN signal. So PSEN, we can say it is used as a read control for reading the program memory, whereas the microcontroller, it can both read and write the internal RAM, that is random access memory. So for read and write operations with the internal RAM, we have the separate read and write control signals. Read RD bar, it is for read, and WR bar, it is for the write operations. Now as in this microcontroller, we have only the memory of, and this memory is either external or the internal. So if we talk about the interfacing, that is input output ports interfacing, so in the case of microcontrollers which are like this 8051, so only the memory mapped input output interfacing is possible. So now let us study this program memory in detail, that how in 8051 this program memory is divided. We have the program memory as 64 kilobytes, and we are having the 16-bit registers for addressing this program memory. So 64 kilobytes of program memory is there. So if we talk about the addresses, they will be the 16-bit addresses, and these 16-bit addresses will start from 000H to FFFFH. Okay, and we have already studied that if we want to, so this complete 64 kilobyte of memory, if we want to address it, we have the address range from 0000 to FFFH. Now as we have studied that the program memory, it can be read, and it can be read only. Okay, the programs can only be read from it. Now, and we use the signal PSEN, that is program store enable, to store the programs in it. Okay, now let's see that how this PSEN signal, it affects this program memory. So we are having the complete 64 kilobytes of memory. So this complete 64 kilobytes, out of this we have the 4 kilobytes of memory, which is acting as the internal, and remaining 60 kilobytes of memory, it acts as external. Okay, so when this PSE signal it is made high, then this 64 kilobytes of memory, this 64 kilobytes of memory, it will be divided into two. 4 kilobytes will be internal and 60 kilobytes will be external. And when this PSEN signal is low, then this 4 kilobytes of internal memory, it will be ignored and we have the complete 64 kilobytes of memory as external. So in the 8051, we can divide this ROM program memory into two parts, either internal or external, depending upon the condition of this PSEN signal. If this PSE signal is high, high means that it is connected to the plus 5 volts, or we can say that its value is made 1. Then the 64 kilobytes, it will be divided into two parts, 4 kilobytes and 60 kilobytes. 4 kilobyte will be internal, so its addresses will be from 0000 to 0FFF. Okay, 4 kilobytes are there, and remaining 60 kilobytes starting from 1000 till FFFF, we will have the external memory. And when this PSEN is low, we will have the complete memory 64 kilobytes is external, that is 00000 to FFFF. Okay, so this was the program store enable signal and the program memory. Now coming to the block diagram again. In the block diagram, we have the interrupts blocks also. So these interrupts, because each interrupt is assigned a subroutine, and whenever that interrupt is executed, the subroutine will be called, which is stored at some specific memory location. So for every interrupt in the 8051, we have a specific memory location where the subroutine is stored. So that lower part of that program memory, that is in this memory location, that is 0000 to FFFF, the lower part of this program memory, it is used to store the subroutines for the interrupts. So we can say here that lower part of program memory is used to store the interrupt structure. So this was about the memory organization, that how the program memory and data memory, they are assigned in the 8051. So let's again come to the block diagram or the architecture. In the block diagram, when we started, I have told that there are various blocks in it, and we studied the description of all the blocks. First we studied the arithmetic and logic unit, accumulator, B register is there, program status word, how the 8 bits they indicate about the conditions of the flags, and then stack pointer, program counter, data pointer is there. Then 4 ports, each port is having a driver and a latch, it is given here. Then instruction register and timing and control unit, which provides the control signals to all the blocks of the 8051. And then the memory, that is ROM and the RAM. How the RAM, it has the address register, and ROM, for ROM we don't have any address register, we can only read the ROM memory. So this was the architecture, or we can say the block diagram of 8051 microcontroller. So I hope that this topic is clear to you. Thank you.